As we said last time, we're going to start talking about structure. We're going to start with atomic structure. So without further ado, let's get our notes up in front of us. Okay, so when we're looking at atomic structure, that's really synonymous with elemental structure. And to understand atomic structure and elemental structures, to know how to answer the question, what makes up the atoms / elements in the molecules we're studying. Excuse me. This is a really exciting field of, there is a really exciting field called particle physics, which looks at all of the particles and their physical properties in detail. And it's really kind of this that defines our current understanding of atomic and elemental structure. We're going to take a step back from modern particle physics and only focus on a few subatomic particles. So these are going to be the subatomic particles to worry about. In the subatomic particles, we probably all have heard of them. They are the protons, neutrons, and electrons. Before we look at them in more detail, I just want to define this term subatomic particles really quick. We're going to use that quite a bit. These are the particles that make up atoms. And being able to use the term subatomic is actually sort of helpful. So a nice little note to kind of digest somewhat. So the number of protons, the number of each subatomic particle, I should say, number of subatomic particles in an atom determines its properties. So simply by changing the number of each of these subatomic particles within an element, maybe just changing one, like just the proton count, or changing electron count, or changing all of them, will change greatly the properties of the element or the atom that you're studying. And so to look at this, what we want to do, or I guess to really understand why this is the case, we should look at the properties of the subatomic particles. And to do that, I'm going to make a table. And so in this table, we're going to list, I'm just going to go on to the next page. To do that, I'm going to create a table, and the rows will be entitled mass, charge, location, and not really a property, but something that's helpful is the symbol or notation, just to help us abbreviate somewhat. So we're going to describe each of these things for the proton, neutron, and electron. Okay, so we have our table made. Let's start filling it out. So the mass, starting with the row, the mass row, what we have is 1 for the mass of the proton. I'm going to add a unit here in a second. 1 for the mass of a neutron, and 1 over 1,836 for the electron. So the unit on this mass will be AMU. Now for the electron, 1 over 1,836 is a pretty small number compared to the number 1. And as a result, we're going to call this essentially 0. We do have instruments, and we do have instruments here at Ripon College that can detect the differences of molecules that have lost or gained electrons, but that's not something we're going to talk about too much in this class. So as a result, we'll mostly consider the electron to be 0 AMUs. So AMU, we'll denote that down at the bottom of our table. That is the atomic mass unit. And it is an SI unit for a subatomic particle. So its true number is the mass of a single proton. Particle physicists found that it was helpful to discuss the masses of the various subatomic particles as just being relative to a proton, where the proton and the neutron are virtually identical, whereas the electron is 1 over roughly 2,000th of that of the proton. So that's where the atomic mass unit unit came about. So for charge, we're going to add +1 for the proton, 0 for the neutron, and -1 for the electron. All of these properties are pretty fundamental, but the charge is most important when thinking about the chemical properties of these things. So that's something we definitely want to get memorized as soon as possible. The location, I think this is interesting to include, and that is, we're going to say the nucleus is the location for the proton and the neutron. And electrons exist in what are called orbitals. We'll discuss what orbitals are in a little while. The symbol or notation for protons, I like to have P with a superscript plus for protons, N with a superscript 0 for neutrons, and E with a superscript minus for electrons. That's just a shorthand notation. If we're describing situations where we want to think about subatomic particles and how they're behaving within molecular systems, it's helpful to just write these out. In particular, the notation for the electron. So what we see here are masses, which are basically weights of our subatomic particles, charge, which we'll get to in a second, location, and symbol. Hopefully location, even if we don't really know what a nucleus or an orbital is, hopefully location is something that we can at least grapple with. It's where something is positioned within, in this case, the atom. The symbol is just something that we define to help us communicate things faster. Charge may be a little bit more vague. I'm sure we've all heard of charge, and we've seen pluses and minuses on various useful things like batteries and that sort of thing. But what is charge? We noticed that in our table, it didn't actually have a unit involved or attached to it. So what is charge? Let's try to address that question. So charge tells us that protons are attracted to electrons, but protons are also repelled by other protons. So it's this fundamental physical property of, in the case of charges, opposites attract and likes repel. So that's what really a charge is. So charge, keeping in mind that opposites attract and likes repel, what charge tells us is that the proton and electron have opposite charges. Sometimes I like to circle the plus and minus on the proton and electron just to make sure that we can tell that the electron, the negative on the electron is actually a negative and not just a line that we accidentally drew. So Protons and electrons have opposite charges, and as a result, protons and electrons, are attracted to each other. So what is charge? Charge is something that allows us to understand how things are going to interact. For example, protons and electrons will be attracted to each other. Now, again, keeping in mind that while opposites attract, likes repel, this also tells us that similarly, protons are repelled by other protons, and, sorry about that, electrons are repelled by other electrons. Why? Because they have the same charge. Both of our two electrons that we're considering putting close together have the same charge, so they're going to repel and bounce away from each other. We see that when we have when we have two magnets that we're pressing together that have identical poles. Okay, so protons are repelled by other protons, electrons are repelled by other electrons. What about neutrons? Neutrons do not interact with other subatomic particles and really that interaction is electrostatically interact. That is to say that opposites attract and vice versa, likes repel. So when it comes to charges, we don't worry about how neutrons are going to interact. According to charges only, we're not going to see an attraction or repelling when we put neutrons close to other electrons, protons, or neutrons. There are other forces at play here called nuclear forces, which help kind of govern how atoms will bind together when there are neutrons and protons put in close proximity. But we're not going to worry about the electrostatic contribution of how a neutron is interacting in those sorts of situations, because, and we reflect that by saying that neutron is defined to have zero charge. It's not repelled or attracted by other subatomic particles, whether they're protons, neutrons, or electrons. Okay, so going back to the other subatomic particles, it's hard to know what the most important subatomic particle is. Turns out for this class, in the next few lectures, we're going to be focusing a little bit more on neutrons, but that's just sort of cleaning up for introductory chemistry when we talk about isotopes and radioactivity and that sort of thing. But after that, we're going to move away from neutrons for the most part and focus only really on protons and electrons. These are the things that, in terms of introductory chemistry and introductory organic chemistry for sure, are really the most important players. So thinking about these two types of subatomic particles, let's go back to the periodic tables. The periodic table shows how many protons an element has by listing its atomic number. So its atomic number. So for example, I know I haven't shared the periodic table that we're going to use in this class, but don't worry so much about that. Periodic tables are everywhere. Let's just focus on one element, and that element is going to be carbon. So carbon, if we look for it on a periodic table, we can find it as being a square with the letter C. And in the square with the letter C, in the periodic table that we're using, we see a 6 above that letter C. There's a different format of the periodic table. It probably should also have the number 6. And we're also going to see, in our case, down below, a number 12.011. These are all very important attributes of carbon. There may be other things included, but these are by far the most important things. So the number 6 is the atomic number. The atomic number. And what this is this atomic number, very important attribute of our elements, is equal to the number of protons in an element. The letter C is the atomic symbol, and you can think about this as being like the atomic abbreviation. So every element has its own atomic symbol. Some of them are very intuitive, like C for carbon, and Si for silicon, O for oxygen, H for hydrogen. Some are less intuitive in terms of the English language, like Na for sodium, and that sort of thing. In a traditional introductory chemistry class, you may be asked to memorize these sorts of things. Something we're going to talk about next time, but not for today, is the weighted atomic mass. That's very helpful to have in the periodic table, but it's not something that we're going to worry about at this time. So the important thing is to go back to the atomic number. That's the number of protons. And it turns out that this is an important attribute of an element because it doesn't change. Let's put it this way. If the atomic number of carbon is 6, what this is saying is that every carbon atom in the universe has 6 protons. Because we say that according to the periodic table, the atomic number, which is 6 for carbon, defines how many protons are in that particular element. So every carbon atom in the universe, not just on planet Earth or in our laboratory setting, for example, everyone in the universe has 6 protons. Similarly, every atom in the universe with 6 protons is a carbon atom. There are no exceptions to this. Based on how the atomic number is defined, every element in the universe with 6 protons has to be a carbon atom. It has to. And every element that is a carbon atom has to have 6 protons. The other subatomic particles can fluctuate around quite a bit, but not the protons. If you change the number of protons, you change the identity. So for example, there are some radioactive processes where you can change. If we take a, let's go ahead and consider let's go ahead and just consider nitrogen. If we take a nitrogen and subtract 1 P plus from the nucleus, we must then have what type of element or what atom will we have in our possession? Okay, so what element must we have if we take a nitrogen atom and subtract 1 proton? Well, nitrogen on the periodic table is close to where we were looking before. It has a 7 above it. That's its atomic number. We have 7 protons in the nucleus of nitrogen, and it has an atomic weight of approximately 14. Okay, so we have 7 protons with our nitrogen atom, what we're going to do is we're going to cross one out, -1p plus. That's going to give us a new element with 6 protons. So we have now 6 protons in our atom. We took 1 proton out of our nitrogen atom and we got to a 6 proton atom. And what does that mean? That means it's now a carbon atom. Because every element in the universe with 6 protons is a carbon atom. Okay, so hopefully we can start to appreciate the importance of protons. It's really the identifier of an element. Every element's identity, every atom's identity is controlled by the number of protons that it has. But we'll talk in upcoming lectures about fluctuating the other types of subatomic particles like neutrons and electrons. Thanks so much for listening.